Well, Professor Caleb, back at it again with Gus. Today we'll be doing question. Let me check. I think it's 24. Sorry. Yeah, question 24 of the bonus questions. And Gus needed help doing this problem. So let's read it out, Gus. The problem is a 20 grams of gas that has a specific heat of 0.205 calories per gram Celsius absorbs heat from its surroundings. That's very important, Gus. It undergoes a 25 Celsius degree increase in temperature. Simultaneously, an external pressure of 2 atm or accident pressure, whatever, compresses the gas from 3 liters to 2.7 liters. Calculate the change in internal energy. Now I'm going to real this problem. I'll change the camera real quick. Nah, it's fine. It's fine. Anyway, sorry. When I first read this problem, I had a lot of trouble too, Gus. Scared me a little. But it really isn't that. It really isn't that hard. Let's look at the question again. It tells us to calculate the change of internal energy. So we know work is done on the system because external pressure compresses the gas. So work is being done in the system, and we know it has a change in temp and heat because it takes in heat from its surroundings. It has a temperature increase. So all we're looking for, Gus, is change. Ooh, this marker's not that good. Hope you guys can see this. I don't know if we did this. Change in internal energy equals Q plus W. And Q is heat, W is work. Delta E is change in internal energy. So rather simple. All we have to do is find out how much heat was absorbed by the system and how much pressure is done onto the system. And this is important because from basis, we can already establish that our Q is going to be positive because it's absorbing heat from its surroundings. It's an endothermic thing because it's taking in heat. And we also know that work is going to be done on the system because the gas is compressed, meaning work is also going to be positive. So let's go ahead and start. Let's look at our, let's go ahead and find how much heat is in the system because that's probably the easiest. So we have 20 grams of gas. 20? I mean, you should got a better marker. 20 grams. Let's check if you guys can read this. I don't know if you can. Sorry. 20 grams of gas. And the specific heat is 0.205 cal per gram of Celsius. Right? And it has a temperature increase of 25 degrees. So, yeah, 25 Celsius. And change in temperature is delta T equals TF minus T initial. And since this is a positive, we can presume, well, we know that the final temperature is greater than the initial. No, you know what I'm saying. This doesn't matter. Yeah. Anyway, that's all our numbers. And to find Q, our heat, we use the equation Q equals M times specific heat times delta T. And Gus, you might think, well, let's just plug in our numbers, right, Gus? We have our specific heat, our mass, and our change in temperature. However, Gus, is a very important fact. Usually we get our readings of energy in joules, and that's obviously not in joules. So we'll convert this, specific heat in calories, to joules. And Gus, if you recall, 1 calorie is equal to the amount of energy required to raise 1 gram of water by 1 degree Celsius, correct? And what's the degree of water again, Gus? That's right. It is 4.184 joules per gram of Celsius, right? So it takes that many joules to increase the temperature of water by 1 Celsius. per 1 gram. Yeah? That happens? So, which means, Gus, we can use this knowledge that 1 calorie, because we know 1 calorie is equal to this. We know that 1 calorie is equal to 4.184 joules, right? To convert this to our amount of energy to our specific heat in joules. So let's go ahead and do that. So 0.205 calories per grams of Celsius. Dimensional conversion analysis, whatever. 1 calorie is equal to 4.184 joules, right? Make sure you can see this again. Sorry, the black marker, I know it's there, obviously. You're probably thinking, why did you just use the black marker? It's kind of bad. So I'm using the green one. Anyway, this cancels, so this times 4.94. Oh, sorry for the burp. A bit humorous. And we get, I'm sorry. Let me go off screen for a second while I get my calculator. Should have set up better. It's kind of weak in this, to be honest. They really rehearsed. I apologize. So 0.205 times 4.184. And this will equal 0.8. Sorry, I'm thinking 5.8 joules per gram Celsius. Yep. So this is our specific heat in joules. Let's go ahead and erase this. 5.8 joules. Give me a second while I erase, because we're going to need a lot of room for this. Anyway, moving back, so Q is equal to mass times specific heat times delta T. And now that we have what specific heat in joules, all we have to do is multiply 20 grams by this, by this. So, kind of smart, watch this. I don't even have to rewrite it, I just write a dot for reason. And we know the 20 grams will cancel out with the grams down here. Celsius will cancel out with that. All we're left with is the only unit we're left with now is joules, meaning we'll just get Q. So 20 times 0.858 times 25 for 29 joules. So our Q is equal to 429 joules. Yep. However, obviously we need to calculate work done. So let me erase my work real quick. And now goes to the hard part. I don't say it's hard. It's what confused me at first, to be honest. So, an external pressure of 2 atm compresses the gas from 3 liters to 2.7 liters. Okay, so the formula for W is W equals negative P times delta V. Delta V is change in volume, and negative P is pressure, basically. Or negative pressure, rather. So, our original problem is there's 2 atm compresses the gas. So let's analyze that. If work is being done on the system, or like say for example, gas is compressed, that would mean that the work done is going to be positive. I know I said that, I'm just trying to elaborate further. You'll see why in a second. Anyway, so I have to think for a second. Sorry guys. Oh yeah, sorry. 2 atm. ATM just stands for apparent pressure. So we're just going to plug in all our numbers. So we had 3 liters. Well, first let's calculate change in volume. So originally we had 3 liters went to 2.7. So 3.0 minus 2.7 equals 0.3 liters. Sorry, I almost forgot to get it there. Y'all see that? Yeah, you can. Oh, sorry. For some reason, for me, when I do the recording, the webcam is flipped. I don't know why, so I can't see how I actually should look. So everything's gonna be like reversed, so I can't tell if y'all can really see it. So I apologize. Something's a bit hard to see. I literally cannot tell until after I finish. But anyway, sorry. I'm droning on, taking too long. Anyways, go ahead and plug our numbers in. So I'll do it in the middle so it's easier to see. So negative 2 ATM times 0.3, and that gives us 2 times 0.3 equals 0.6 ATM. Oh, wait, I didn't think it. Something's off. Think. Oh, wait a minute. Yeah, something's off. Okay, sorry again. I remember now. Excuse all my rambling. So remember I said earlier how since work is being done onto the system, work is gonna be positive. Well, P is gonna be positive now because the gas is being compressed. Sorry, that is my bad. I really apologize. Yeah, I was wondering. So basically just erase the negatives, and we're left with 2.0 times 0.3 equals 0.6 ATM. Really apologize for that. Sorry for the confusion. I'm gonna re-say that. What makes work positive in this case is because gas is compressed. And I said it like 5 times, but I really want to reiterate so I don't confuse anyone. So yeah, 6 ATM times liters. Ooh. Only not forget my units. Sorry. So our work is equal to 0.6 ATM times liters. Well, as we said earlier, we kind of want our stuff in joules. So, but thankfully, there's a direct conversion from ATM times liters to joules. So basically, I'll write it over here. 101.325 joules is equal to 1 ATM times liter. So we're just going to plug that into our conversion to convert this to joules. 101.325 joules per 1 ATM times liter. We plug in our ATM times liter, and this will give us well, hold on, 1 second. Just to make it easier, I'm gonna add another sig fig to the end of this. So we have 2 sig figs. So I can write my answer as 61 joules. A little bit cheating, but I think it makes more sense this way. Anyway, so we calculated our work, which is W equals 61 joules. Crazy. Now we just plug into the formula Q. So 429 joules plus 61 joules is equal to, drum roll please, Gus, 490 joules. So our change in energy of the system is, our internal energy is 490 joules. Yep. Now, for example, if gas was expanding, that means work is being done by the system, and it would lose energy. Like if you think about it logically, if I were to push this, I use my energy. But if this gun slams into me, work is being done onto me. Yeah. And honestly, if I touch something really hot, my hands can get really hot, so I absorb energy. But if I touch something really cold, I'm gonna lose my heat, and that cold thing's gonna gain energy. That's basically why. Sorry, I kind of went way too long with this. Sorry if it's hard to read. Kind of didn't prep for this at all. Thank you guys, and thank you for all who actually watches these videos.